Hi you guys, this is Miss Gariano, and in this video we are going to be looking at a third type of asymptote called a slant asymptote, or also known as an oblique asymptote. So we already know two types of asymptotes. We have our vertical asymptotes and our horizontal asymptotes. So vertical asymptotes come from when the denominator is equal to 0 and where there are no common factors. Right? So if we had a common factor in the numerator and denominator, they would cancel out and create a whole instead of a vertical asymptote. Horizontal asymptotes come from comparing the degrees of the numerator and denominator. So you guys already know how to find vertical asymptotes and horizontal asymptotes. So what I am going to be showing you today is how to find slant asymptotes. So slant asymptotes have are more similar to horizontal asymptotes than they are to vertical asymptotes. What we are going to be doing is comparing the degrees as well, but this happens so if we have something of the form y equals ax to the m over bx to the n, and there could be other stuff in the numerator or denominator, but these are assuming the highest powers. So we know that from finding horizontal asymptotes, if m is greater than n, we do not have a horizontal asymptote. However, and there's the others, so if n is greater than m or they're equal, we have a horizontal asymptote. However, if m is 1 larger than m, so m is 1 larger than n, so we could say that m equals n plus 1, we are going to have a slant asymptote. So it's not a horizontal asymptote because it's something more on a diagonal line, and we have a way of finding it, and we are going to utilize our favorite long division to find the slant asymptote. So I will be showing you that with an example. Alright, let's look at an example together. So we want to find the vertical, horizontal, or slant asymptotes for the rational function, and then use these to sketch its graph. So let me get some graph paper up here so we're ready to go. So to find our vertical asymptotes, we of course want to look at the denominator of our function here and see where it will equal 0. So we want to know where x plus 1 is equal to 0. So I can subtract 1 from both sides, and I see that x will, if x is -1, our denominator will be 0. And of course we want to make sure that this is indeed a vertical asymptote and not a whole. So we need to make sure that this factor is not going to cancel with anything. So I'm going to rewrite our function in factored form. I notice there's an x in common in both terms, so I can factor out an x. And then our denominator is already as factored as it'll get. So I see that indeed there are no common factors, so this is going to be a vertical asymptote. Alright, now I can look for my horizontal or slant asymptotes. So my horizontal or slant, right? It has to be one or the other because they come from the degree. Asymptote. We are going to compare the degree of the numerator with the degree of the denominator. So the degree of the numerator is equal to 2. And the degree of the denominator is equal to an understood 1. So since the degree of the numerator is just 1 larger than the degree of the denominator, this means that I have a slant asymptote. So we are going to utilize long division to find the equation of our slant asymptote because it's a diagonal-ish line. So I'm going to go ahead and clear away this work for a second so I have room to do my long division. So to do the long division, I am going to take this equation here, this quotient, and I'm going to turn it into a long division problem. So that means I'm taking x squared minus x and dividing it by x plus 1. So with long division, if you remember right, this is asking x times what will give me x squared? Well, x times an x will give me this x squared. So then I'm going to take the x and multiply it through by this factor. So x times x gives me x squared. X times 1 will give me a x. Now with long division we are going to be subtracting, so I'm going to subtract this whole thing, and I like to think of distributing the negative sign, so that'll make this a negative and this a negative. So I get x squared minus x squared is 0. Negative x plus another negative x is a negative 2x. And we can imagine this as a plus 0 and drop that down. Now we're going to do a similar thing. We're asking x times what will give us this negative 2x? Well, we need to multiply it by a negative 2. Then we take this negative 2 and multiply it through by this factor. So negative 2 times x will give me a negative 2x, and negative 2 times a 1 will give me a negative 2. And again, I am going to subtract. So I like to think of distributing this, and I get negative 2x plus 2x is 0, and 0 plus 2 is 2. So I end up with a remainder of 2 over x plus 1. But when I'm finding this slant asymptote, I really do not care about this remainder here. All I really care about is this x minus 2, because that tells me the equation of my slant asymptote. So my slant asymptote is the line y equals x minus 2. Alright, so let's go ahead and add that to what we had. We know our slant asymptote is going to be at the line y equals x minus 2. Alright, so let's go ahead and plot our vertical and our horizontal asymptotes. So we know that we can find our vertical asymptote at the x equals negative 1. So right here. And we can find our slant asymptote given this line. So this is just a linear equation. So this minus 2 tells me my y-intercept. So I'm down here at negative 2. And then I'm going to, the slope here is 1 over 1, so I'm going to rise 1 and run 1. So rise 1, run 1, rise 1, run 1. So it's just a nice straight diagonal line. So I can go ahead and add in my line here, my asymptote, which is going to go across like that. Alright, so now that I have my two asymptotes plotted, I want to pick some convenient values so I have a better idea of what's happening kind of in between these slices of our asymptotes. So I'm going to clear away our asymptote work so that there's room to see what else is going on. Alright, so we want to create a table of values. So our x's and our y's, and I'm going to pick some convenient values. So I want something to the left of our vertical asymptote, so -2 would be good. I want something to the right of this vertical asymptote, so 0 would be good. We could do 1 as well, and then maybe 3 to get something to the right of our slant asymptote. Well, potentially right. It's, getting further to the end. So I'm going to do these 4 values. So that's a -2, 0, 1, and 3. So at -2, if I plug that in, I get a -2 squared minus a -2 over -2 plus 1. So -2 squared is 4, minus a -2 is plus 2, and then -2 plus 1 is a -1. So I get a -6 as this point. So -2, -6. So there's that point. And then for 0, I get 0 squared minus 0 over 0 plus 1. So I really just get 0 over 1, which equals 0. So at 0, I'm at 0, 0, right here. Then at 1, I get 1 squared minus 1 over 1 plus 1, which is going to be just 1 minus 1 is 0, and 1 plus 1 is 2, which is really just 0. So at 1, I'm still at 0. Then at 3, I get 3 squared minus 3 over 3 plus 1. So 9 minus 3 over 4, which is 6 over 4, which is 3/2. So at 3, I'm up at 1.5. So right here. Alright, so now that I have some values, I'm going to play the keep inside the asymptote line game. So I know that I'm going to curve towards the horizontal asymptote, or sorry, the slant asymptote here on this side, and then I'm going to approach the vertical asymptote. So this side's going to be doing something like this. And then up here, again, this side, this branch is going to approach my vertical asymptote here, and then approach this slant asymptote here. So by using my asymptotes as a guide, I was able to quickly get the general shape of this graph. And without knowing our slant asymptote here, it would be really difficult to get the shape of this right branch. We might think that it does something like this, or we just really don't have a guideline. So it could do a lot of things, but once we know the slant asymptote, it's really easy to go, oh, I know it's going to, kind of come down and pick up really fast and follow this line. So I hope this example makes sense and that it will help you complete your few practice problems on this assignment.